Today we are going to learn about mastering matrix multiplication in NumPy. We will explore efficient matrix multiplication techniques, understand the use of dot and matmul functions, and tips to enhance computation performance. Welcome to our session on mastering matrix multiplication in NumPy. In today's video, we'll uncover the importance of matrix multiplication, especially in the context of data analysis and machine learning. Matrix operations are fundamental in scientific computing, where accuracy and performance are vital. By mastering these techniques, you'll enhance your ability to handle large-scale data processing tasks efficiently. We'll delve into NumPy, a powerful Python library that facilitates efficient numerical operations, including matrix multiplication. By the end of this session, you'll be equipped with optimized techniques for performing matrix operations crucial for data transformations and scientific computations.
Matrix multiplication is a core operation in many areas such as data science, engineering, and computer graphics. Let's start by understanding what matrices are. They are two-dimensional arrays of numbers. In matrix multiplication, the number of columns in the first matrix must be equal to the number of rows in the second matrix. NumPy, a fundamental package for scientific computing in Python, provides powerful tools to handle such operations. Before we dive into matrix multiplication, ensure you have NumPy installed. You can install it via pip using the command pip install NumPy. Once set up, you can create matrices using NumPy arrays. NumPy provides an array data structure that is more efficient than Python lists for numerical operations. Creating a matrix in NumPy is straightforward. Simply use the NumPy.array function with a list of lists representing your matrix. Understanding these basics will pave the way for more advanced operations. The dot function in NumPy is an efficient way to perform matrix multiplication. The dot product is a fundamental operation where two equal-length sequences of numbers are multiplied and then summed. In NumPy, the dot function handles this operation seamlessly.
To illustrate, consider two 2x2 matrices, A and B using NumPy. You can compute the dot product by calling np.a, b. This function takes care of the underlying computations, ensuring they are performed efficiently.
Unlike manual computation, which requires iterating over rows and columns, dot abstracts this complexity, making your code cleaner and faster. This exemplifies NumPy's power in simplifying complex mathematical operations. Comparing the output of np.dot with manual calculations, you'll notice the consistency and reliability of NumPy's implementation. Leveraging dot in your projects will save time and reduce errors, particularly when dealing with large matrices.
Broadcasting is a powerful concept in NumPy that allows you to perform operations on arrays of different shapes. It works by stretching the smaller array across the larger one, enabling element-wise operations without the need for explicit loops. This feature is crucial for efficient computation, especially in scenarios where array dimensions don't initially match. For instance, consider adding a scalar value to a matrix. Broadcasting automatically applies the scalar to each element of the matrix. While broadcasting can significantly enhance performance, it's essential to understand its limitations. Not all operations can be broadcast, the arrays must be compatible in certain dimensions. A common practical application of broadcasting is in normalizing data, where each value in a dataset is adjusted by a common factor. By leveraging broadcasting, you can achieve these operations succinctly and efficiently, reducing the computational load and enhancing the performance of your data processing tasks.
The matmul function in NumPy is designed for matrix multiplication involving higher dimensional arrays. While the dot function works well for two-dimensional arrays, matmul extends this capability to multi-dimensional arrays, where it performs a matrix product between the last two dimensions of the inputs. This is particularly useful in advanced applications like machine learning, where tensors, or multi-dimensional arrays, are commonly used. Suppose you have three-dimensional arrays representing batches of data. With matmul, you can perform batched matrix multiplications efficiently. One key difference between dot and matmul is that matmul does not handle element-wise multiplication for one-dimensional arrays, a behavior specific to dot. When using matmul, ensure your arrays are appropriately shaped to avoid errors. Following best practices, such as validating the shapes before computation, will help in leveraging matmul effectively. By understanding and utilizing matmul, you can handle complex data structures with ease, improving the scalability and performance of your applications. Choosing between dot and matmul depends on the specific requirements of your computation tasks. Both functions are optimized for performance, but they serve slightly different purposes. Dot is versatile for two-dimensional arrays and can handle one-dimensional array dot products. Matmul, on the other hand, excels in handling higher dimensional arrays, making it suitable for more complex data structures. When comparing the performance of these functions, it's important to consider the context. For simple two-dimensional matrix multiplication, dot might be slightly faster due to its simplicity. However, for batched operations on higher dimensional arrays, matmul is the go-to function. Benchmarking your specific operations can provide insights into which function offers better performance for your use case. Factors such as array size, dimensionality, and specific application requirements will influence your choice. Understanding these nuances will enable you to select the right tool, optimizing the efficiency and speed of your matrix operations. Matrix operations, while powerful, can sometimes lead to challenging issues if not handled carefully. One common pitfall is shape mismatches, which occur when the dimensions of the matrices involved in the multiplication are not compatible. Always ensure that the number of columns in the first matrix matches the number of rows in the second. Another frequent issue is related to data types. NumPy arrays have a specific data type, and operations involving different types can lead to unexpected results or errors. Ensuring consistent data types across operations is crucial. Numerical stability is another important aspect. Operations involving large numbers or high precision can lead to floating point errors. Taking care to use functions that handle these calculations accurately is imperative. Debugging matrix operations can be simplified by printing the shapes and types of your arrays before performing operations. By being aware of these common pitfalls and taking proactive measures to address them, you'll be able to perform matrix operations more reliably and efficiently.
Matrix multiplication is not just a theoretical concept, it has numerous practical applications in the real world. In data transformations, matrices are used to manipulate datasets, enabling operations such as scaling, rotation, and translation. In machine learning, matrix multiplication is fundamental in neural networks, where weights and inputs are multiplied to compute activations. Similarly, in computer graphics, matrices are used to transform coordinates and render images. Understanding how to leverage matrix multiplication in these contexts can significantly enhance your ability to solve complex problems. Whether you're scaling features for a machine learning model or applying transformations to a dataset, NumPy's efficient handling of matrix operations can streamline your workflow. By mastering matrix multiplication, you'll be equipped to tackle a wide range of data processing tasks, making you a more effective and versatile analyst or developer.
Optimizing the performance of matrix operations can lead to significant improvements in computational efficiency, particularly when dealing with large datasets. One key strategy is to understand the computational complexity of your operations and choose algorithms that minimize complexity. Efficient data structures, such as NumPy arrays, are designed to optimize memory usage and speed. Another approach is leveraging parallel computing, where operations are distributed across multiple processors to enhance performance. Libraries like NumPy are optimized for such tasks, utilizing underlying hardware capabilities. Profiling and benchmarking your code can offer insights into bottlenecks, allowing you to focus your optimization efforts effectively. Tools like cProfile in Python can help identify slow sections of your code. By implementing these tips, you can enhance the performance of your computations, making your applications faster and more responsive. This is especially crucial in data-intensive fields where speed and efficiency are paramount.
In conclusion, mastering matrix multiplication in NumPy is a crucial skill for anyone involved in data analysis, machine learning, or scientific computing. We've explored key techniques using dot and matmul functions, discussed the importance of understanding broadcasting, and highlighted real-world applications that demonstrate the power of matrix operations. Efficient matrix computations are vital for handling large-scale data processing tasks, improving both performance and accuracy. As you continue to learn and practice these techniques, you'll find that your ability to solve complex problems will grow. Remember, continuous learning is essential in this rapidly evolving field. We encourage you to explore additional resources and keep experimenting with different approaches to deepen your understanding. Thank you for joining us on this journey to mastering matrix multiplication in NumPy.